Okay. In this lecture, we will learn the technologies about the asphalt materials. This one is very important for the design of the flexible pavement. With that, basically in this lecture, we will focus on introduction about some features of the asphalt materials, and more importantly, we're gonna explain how we can conduct the SUPERPAVE specimen and show the steps to prepare the SUPERPAVE specimen step by step. So the first thing we have to ask is about what is asphalt. The asphalt is actually a material made up of predominantly hydrocarbons. You can find out that almost 82 to 88% of the asphalt will be the carbon, and around 8 to 11% will be the hydrogen. And there are also some small amount of the sulfurs, nitrogens, and oxygens. The percentage is very low, which is they are all less than 10%. For the sulfur, it's usually below 6%. For oxygen, it's less than 1.5%. For nitrogen, it's less than 1%. And it also contains very little metals like the vanadiums, the nickels, the irons, and so on. The asphalt is widely applied for the pavement design, and especially for the flexible pavement. It will be the major materials for the asphalt layers or the surface layers of the flexible pavement. By applying or mixing the asphalt with some aggregates, we can get a better properties in the penetration, viscosity, and the shear modulus. So with that, we can improve the stiffness, or we say that the hardness of the pavement surface, and then the pavement structure can last for a longer time and is able to support higher load or higher volumes of the traffic load. Originally, the term asphalt refers to some black cementitious materials, which varies widely from in the consistency from the solid to semi-solid at the normal temperatures. You might find out some nature asphalts. They could be you can find out some if you search online, you will see some very large asphalt lakes. There's one very famous asphalt lakes in Los Angeles. It's La Brea Tapiz. This would be a small asphalt lake in the city, and there are also some other very large asphalt lakes in the Caribbean area. And also the asphalt can be extracted from the petroleums. And this would be the most common asphalt materials that we're going to use in the current pavement design. Generally, there will be three types of the asphalts. They could be the natural rock asphalt, which would be the rock deposits containing bituminous materials. This one has been used for the road surface a lot, and especially for those regions with locally available rock asphalts. And the second one is the native asphalts, which would be some of the asphalt lakes in Trinidad or some Caribbean areas. And this would be the major source of the asphalt in the early days pavement design. And the last source, which would be the major source for the modern pavement design, that would be the asphalt from the petroleums, and it actually comes from the distillations of the crude oils. And this, as I say, that this is the most common materials we're going to use in nowadays. There will be some features about the asphalt binders, which we say that the asphalt layers for the pavement. Usually the asphalt is very sensitive to the temperatures. When the temperature is low, the asphalt would be stiffer, and when the temperature gets high, even around 40 to 50 degrees, the asphalt can melt and the road will becomes very soft. And the second features of the asphalt layer or asphalt binder will be the viscoelasticity. And this one means that the asphalt could act as some fluid at a very high temperature, for example, around 100 degrees. This is only this might happen at some very hot areas in the world. And it will be an elastic solid, which means that it's less elastic at low temperature when the degree is less than 0. This is another significant features we have to consider to design asphalt pavement with the at the cold regions, especially in Canada. We have the long durations of the winter season, and the temperature can easily drop below 0 degrees. And the other issue related to the asphalt layer is called the aging. Actually, the asphalt layer is always exposed to the air, so the oxidation is one issue about the asphalt, and this one can cause the edge hardening, which will reduce the elasticity modulus of the pavement structure, and they will create some fatigue crackings or some other type of distresses when the pavement structure is old. Generally, there will be for the asphalt binder, we will usually mix the asphalt with some aggregates. We also need to carefully select the aggregates to get some desired features or get some desired aggregate behaviors. For those aggregates, there could be some natural rocks or natural sands. There could be some processed or synthetic materials, or there could be some recycled materials from the old pavement structure. And usually to select the aggregates, we have to make sure that they can provide enough shear strength so that they can support the repeated load from the large trucks and the passenger cars. In addition, to measure the shear stress, we usually need to think about the internal frictions, and that one would be one important property for the aggregates. And usually for the aggregates, if those aggregate particles will be the cubical, they have some very rough textured surface, then they can offer more resistance, and with that the shear strength will be larger. So this means that we need to check the shape of the aggregate particles. We need to find out, identify the faces of the particles, the shape of the faces and the angles of the particles to identify or to determine the shear strength of the aggregates. And if we have the rounded aggregates, then it probably means that the shear strength would be very low. For example, for the natural sands, usually their surface is smooth, and this indicates that they are not appropriate for the aggregates in the for the asphalt binder. So those would be the features we have to consider for the aggregates to use for the asphalt layer or the asphalt binder. And in the design of the asphalt binder, we're gonna mix the pure asphalt with the aggregates. And this kind of asphalt mixture will need to design to solve some major pavement distress, such as the pavement deformation, that will be the rotting, the fatigue cracking, and also the low temperature cracking. This is one important factor we need to consider because the asphalt will be significantly affected by the temperature. And for the hot mixed asphalt mixture design, we want to develop an economical blend of the aggregates and asphalt binder so that we can meet the design and the functional requirements. So the selections of the aggregates, the amount of the asphalt should be carefully considered based on the traffic conditions, the weather or the temperature conditions of the pavement, and the thickness or the load, the lower layer structures, and so on. And historically, there will be two commonly applied methods to design the hot mixed asphalt. The one is we have the Marshall mixture method and the HVEEM mixture design method. I'm gonna introduce the advantage and disadvantage of these two methods later. If you are interested about the details of these two methods, you can search online or go through the reference materials I put in the first lecture to see how these two design method is conducted. But for nowadays, most of the hot mix asphalt is designed based on the SUPERPAVE, which is also called the gyratory mix design. And this is the information we're gonna introduce in this lecture. And there will be more details about each step of the design. So for the first, for the Marshall mix design, there will be some advantages and disadvantages. For the advantages, like with the Marshall mix design, we're able to control the density and void properties of the asphalt mixture. It's quite easy for us to find out these values. And the instrument to design the specimen is very simple and it's easy for us to get. It's not expensive and it's even portable, so that it can bring the device outside or even in the field to design the specimen, the asphalt binders. And the disadvantage is like this one does not consider the impact of the compaction, and with that the densification from the compaction in the real world will not be cannot be modeled with this design. And the also in this design, there's one feature called the Marshall stability. This one is measured in the design, but it does not represent the shear strength of the hot mixed asphalt. So it might not be appropriate, or it cannot represent the actual performance of the asphalt binder in real world. The next method is called the HVEEM mix design, and this one overcomes a lot of drawbacks of the Marshall method. With this, in this design, the is especially considered the specimen or the asphalt binders consider its resistance to swell in presence of the water, and it has the needing laboratory compaction simulation so that we can understand the impact of the repeated load to the asphalt binder. Also, the HVEEM stability, which is the feature that we measured from the HVEEM mix design. This one is a direct measurement of the internal friction component, and which means that we can use this stability to show the or to estimate the shear strength of the design. But there's some clear disadvantages. First of all, the test equipment is very expensive and it's very large. So you can only do the design in the lab. You cannot go to the field. And for the selections of the binder content, which means that the amount of the asphalt content, how much of the asphalt should be combined with the aggregates, this selection is too subjective. You have to rely on the past experience of the pavement engineers. Does not have any mathematical models or some formulas to tell you how you're going to get or what kind of amount of the asphalt content should be selected. So this is also a very obvious disadvantages of the VM mix design. So in order to improve this all the design methods, the SHARP, the strategic highway research program, proposed a SUPERPAVE design, and this one can improve the performance and durability of the pavement structures, and also they will actually consider the properties of the asphalt specifications and use these specifications in the lab analysis and also simulate the field performance of the asphalt binder in the lab, so that we can get a reliable design from the lab and then bring the design to the field. Make sure that the design will work appropriately in the field for longer time. So the SHARP program actually proposed the SUPERPAVE design method, and this one is actually an abbreviation of the superior performing asphalt pavement. It's one of the important products of the SHARP asphalt research, and this kind of product defines the new standard for the aggregates and the bituminous binders, which is the asphalt binders used in the paving. Also, they have some considerations about the mix design changes, how the mixture of the aggregates and the asphalt binder will change the features or change the properties of the sample or the specimens. The SUPERPAVE can have some very good features. First, the SUPERPAVE asphalt binder test can measure the physical properties, which is directly related to the field performance. So this one, so for the features that you measured in the lab, it will be actually the real or close to the realistic features in the field. And also the SUPERPAVE binder tests are conducted at an in-service pavement temperature. So it's in a real temperature, like if the temperature outside is 20 degree, we'll do the experiment about 20 degree in the lab. And also it has gyratory compactors to reproduce the impact of the repeated load, and we're going to use this compactor to prepare the how to mix the asphalt specimens. For the SUPERPAVE mix design, there will be some steps, and this is the part I'm going to introduce in the next in the lecture today, and also 2 more lectures next week. It defines the steps, having a clear definition about how to select the asphalt and how to select the aggregate materials. We need to consider the impact of the weathers. We need to consider the features of the aggregates, especially the particles of the aggregates, to make sure that the satisfy the requirement of the pavement in that specific area. And this method will integrate the material selection, the mix design in the whole procedure. And we need to consider the climate conditions and traffic conditions in the field. And of course, we have the in the lab we will do the compaction, which is called the SUPERPAVE gyratory compactor, and that's what you're gonna see in the third lab, the demo lab experiment. And the SUPERPAVE gyratory compactor can be used to design the mixtures that do not exhibit the classic tender mixture behaviors and don't densify to dangerously low air voids and the traffic actions. So you will try to make sure that the specimen is realistic, does not go to some extreme design. And this one is trying to apply to reproduce the real world performance of the asphalt binders, how to mix the asphalt binders under the realistic traffic condition and the realistic climate condition. And actually this kind of design is not only based on the empirical information. It's also based on some physical models. So it's a kind of the combination of the mechanical method and also the empirical method. This is the kind of the combination. So the for the SUPERPAVE mix design, we want to design the asphalt how to mix the asphalt binder so that we can have to ensure the durable pavement, to make sure that the pavement can last for a longer time. And we will also want to the binder to have sufficient stability under the realistic traffic loads. And we also, for the, you might know that for the aggregates, the mixture of the asphalt binder and aggregates, even they're gonna mix together, there still be some air voids in the sample. And we want to control the appropriate amount of the air voids so that we have an upper limit to prevent the excessive environmental damage to the soils and to the groundwaters and so on. We also want to set a lower limit so that we have the room for the initial densification by accommodate to the repeated traffic load. And of course, we want this kind of design to have the sufficient workability to make sure that we can conduct the realistic pavement design in the field. So that will be the general features and requirements of the SUPERPAVE mix design. And from now on, we're gonna go to see the steps to conduct the design. Basically, the SUPERPAVE mix design can be categorized into 4 steps, including the material selection, the design for the aggregated structures, the design of the binder contents, and also the evaluation of the moisture sensitivity. I will go through all these 4 steps one by one, and that will probably take us 3 lectures to finish all of them. First, for the material selection, here we have to consider the selection of 2 materials. The first one is the asphalt, obviously the asphalt binder. The second one is the aggregates. And these 2 will be mixed in the next step. But for the first step, we have to choose the correct asphalt binder, and the binder. Actually, for each type of the asphalt binder or each type of the asphalt, there's one grade, and we have to make sure that this grade can work for all the situations in the designed area. And also we need to select the suppliers of the binder to reduce the cost. If there's any local suppliers, we probably will select them to try to minimize the transportation cost. And for the selection of the aggregates, we want these aggregates to meet the quality requirement of the mixture, and also those aggregates, it's better to select the aggregates from some local companies or some locally available materials. So this is actually still for the budget control. Generally, for the selections of the for the SUPERPAVE materials, we have to conduct a set of the a test, and for those tests, we're going to use the 5 different set of the material equipments. The first two, the rolling thin film oven and the pressure aging vessel. This one is trying to simulate the characters of the aging characters of the asphalt binder. And we also have the dynamic shear rheometer, DSR. This one will measure the property of the asphalt binder at a higher and intermediate temperature. And also we have the rotational viscometer. This one will try to measure the binder property at a high temperature. And the last one, bending beam rheometer, BBR. This one measures the binder property at low temperature. With that, we can try to identify how the asphalt binders is performing under different temperatures from low, medium, and high. And also, we're gonna understand how the property of the asphalt binder is changing over the time. So basically, this figure summarizes those equipments will be applied, those tests is applied to investigate the features of the asphalt binder under the low temperature, high temperature, and intermediate temperature, and also try to check the short-term and long-term aging performance. And of course, we're going to see what kind of the potential distress, like the rotting, fatigue cracking, and low temperature cracking, could potentially applied to the asphalt binder in the future. So with that, we can actually once we conduct all these tests, we can have the features of the asphalt binder and for different type of the asphalt binders. And another thing we have to consider is about the performance grade for the asphalt binder. Sharp program actually defines the performance grade for different asphalt binders based on the and you have to select those asphalt binder based on the climate conditions. For example, the format of the performance grade is usually represented as shown in this one, like the PG64 minus 22. And in this one, PG will represent the performance grade. And the 64 represents the average 7-day maximum pavement temperature. That will be the temperature you will observe in the field where you will conduct the pavement design. And this temperature is in the unit of the Celsius. And the third one, minus 22, will represent the minimum pavement temperature that is going to be observed in the field. So this indicates that if we can find out the average 7-day maximum temperature, you can find out the minimum pavement temperature. Then you can choose the asphalt binder based on this grade. We want to make sure that the asphalt binder, the asphalt binder that you choose can at least cover the maximum and minimum temperatures. So I will show you more details about how to do that. So this is actually the different type of the asphalt binders and their performance grade. So first, for the first row, you can actually get the performance grade. I'll say that the maximum 7-day maximum temperature is 52 degree, and then you can get the the minimum temperature depending on the region that you're going to consider. It could be like a minimum as 10 degree. If it's a minus 10, it means that the minimum temperature is higher than minus 10. If it's a minus 22, means that the minimum temperature should be at least higher than minus 22, and so on. This is also applied for the other categories. So for this one, for example, for the PG 52 minus 40, it means that the average 7-day temperature, the average 7-day maximum pavement temperature should be less than 52, and the minimum temperature should be higher than minus 40. Of course, usually with the larger coverage range, the cost of the pavement binder is or the asphalt binder is higher. And there will be also some other features which will be considered, such as the dynamic shear strength. This one is actually very important for us to understand the shear strength of the asphalt binder. And also we want to, depending on the values that you observe, like we want to make sure that the minimum dynamic shear strength should be higher than 1 kilopascal. And if it does not satisfy, probably it means that we may need to do some modification about the maximum temperature to make sure that it can satisfy those conditions. And also we have another two features, like the dynamic shear strength with the minimum value of 1.0 kilopascal, and another shear dynamic shear, another test at the test temperature of 10 radians per second and so on. If you get these two values with the minimum of 2.2 kilopascal and the 1.0 kilopascal, by finding these two values, you can identify how the asphalt binder is handled with the rotting. And also we have some factors to address the fatigue cracking. With that, you can check the dynamic shear strength with the maximum value of 5,000 kilopascal. And these two, the creep stiffness, if the creep stiffness is less than 300 megapascal, and the direct tension tests show you that the failure strength is higher than 1%. With these two values, you can try to adjust the low temperature crackings for the asphalt binder. So those are all comes from the test with the equipment that I mentioned in the previous page. And the other thing, which is also the most important thing for you to select the asphalt binder, is the temperatures in the field. So we need to think about the temperature, but in reality, we cannot find out a constant value. Instead, at most of the time, we can find out the temperature is in the distribution. For example, for the 7-day average air, 7-day maximum air temperature in Cleveland, Ohio, it follows an almost a normal distribution, and you can find out the maximum temperature with the mean value of 32 degree, and for 98% higher, that will be 36 degree. We need to, as this is distribution, we need to think about which value we have to use. Actually, to determine which value you're going to use, we have to consider the reliability of the design temperature. For example, for the figure below, this one, the distribution on the left shows the distribution of the 7-day maximum average temperature. On the right shows the maximum temperature. On the left shows the minimum temperature. It's also in the normal distribution with a mean of minus 21 degree, and for the 95% higher, the value is minus 29 degree. So if we are provided with this information, we can then try to identify the 98% reliability for the performance grid that I'm going to select for the asphalt binder. Also, I just want to give you another background information of the reliability. The 98 reliability indicates that the temperature, the 7-day maximum air temperature, for the probability of this temperature less than 36, the probability of the less than 36 is 98%. So that will be the probability. But for this one, for the minimum temperature, it will represent that the minimum temperature, the probability of minimum temperature higher than minus 29 degree is 98%. So there's some difference about the reliability for the maximum temperature and the reliability of the minimum temperature. Generally, for the maximum temperature, you have to choose the percentile on the right. For the minimum temperature, you have to choose the percentile on the left. So that's the information that we get for the from the field about the temperature, and then with that we can try to identify or try to choose the asphalt binder based on the temperatures. For example, if we only consider the 50% reliability, then what we can find that is the performance grade is PG 58 minus 28. So it means that the maximum temperature, the 7-day maximum temperature is less than 58 degree, and the minimum temperature is higher than minus 28 for the 50% interval. This is actually different from what you observed in the distribution. You can find that the average value is probably around the 50 degree for the 7-day average 7-day maximum value. For the for minimum value, you can find that the one is probably only minus 24. Ideally, you should have the for 50% reliability, you should have the value as PG 55 minus 24. But this is not; these two values are not realistic. Usually for the performance grade of the asphalt binder, it's changing at every 6 degrees. So we have for the maximum temperature, we have the 46 degree, 52 degree, 58 degree, and 64 degree, and 70 degree, and so on. For the minimum, we have minus 28 degree, minus 34 degree, minus 22 degree, minus 16 degree, and so on. So that's for 7-day. That's for the maximum and minimum. So for 50% reliability, we will choose a range, the grade which can cover 50 to minus 24, and the closest one for 50, the closest one about the maximum value would be 58. So that's what we get as 58. As 58 here. And for the minimum, we have to find out the smallest, the closest one, but of course it's less than minus 24. So what you will find is minus 28. So you can get the grade as PG 58 minus 28. If we are talking about the 98 reliability, 98% reliability, this also applies similarly applies to the selections. So you have to make sure that your selected grade cover the 98 percentage maximum temperature and minimum temperature, or in this case, 98. The closest one for 98 is 46 degree for the maximum temperature. For the minimum, that will be minus 34. So what you get is the PG 64 minus 34. So that's the, I guess I have finished the, we don't have enough time to introduce the rest component. So with that, I will just pause here and see whether you have any questions about the contents. So the in this part, the selection of the performance grade is very important. Especially you need to know how to read the distributions of the maximum temperature and minimum temperature to find out the appropriate performance grade for the asphalt binder. And this is the initial step for you to get the to find out the correct asphalt binder for the SUPERPAVE mix design. Okay. Do you have any questions? Okay. If there's any additional questions, I will probably close the meeting for now. And just feel free to contact me through the email or leave a message on Teams if you have any questions. And I will continue this lecture next week and try to get more information about the SUPERPAVE mix design. And then after that, we will have the midterm review and you can prepare for the first midterm. And of course, more information about the midterm will be set in the announcement. Okay. Okay, I think that will be all. Thank you very much for your attendance. And with that, I will close the meeting today and I'll see you next week.